take that as a no. No questions.
Number 30 in section in the 10-1.
10-1.
We could just go over like one of them so I can see how to.
30. Oh, okay. So, let's analyze. Let me make up a problem here. This is like 30, 10.1, right? Okay. Whenever you're given a set of parametric equations, they each are their own equation. So if I had, for example, x equals 4 minus t squared, y equals, I don't know, sine of pi t. And t goes from -2 to, let's just say 0 to 2. No, let's say -2 to 2. Right? You could graph on an a tx coordinate system. You can graph what this looks like. So if we do that, so this is my output, this is my input, and then we can graph another one for this guy. You with me? Okay, so this is sort of just looking at them as functions of t. This is not the reality of what the end result would be, because the end result is on the xy plane. But this will give me an idea. This is what I was trying to say about if it's a sine function, you know it's going to go back and forth. And I pointed out the fact that you can see from the result that it was doing what we thought it would do. Can anyone tell me anything about this? Parabola, opening, down. Where's the vertex? Yes. When t is 0, you get 4. That's the biggest output it could be, because I'm subtracting nothing. Any other value of t, I'm subtracting something, right? So that's going to be the highest point. And -2, the output is
0.
0, and at 2 it's also 0. So this is what that looks like. So on the resultant graph, if I graph this on a xy plane, I would expect the x coordinate to go from -2 to 4 back to, -2 to 4, let's try this again, Jeff. 0 to 4 back to 0. Right? What's the x doing as t does its thing? X goes from 0 to 4 to 0. So on the x, when I graph this, I'm expecting to see the x part go 0 to 4 to 0. Now the y part's going to do some shit, so it's going to do like that. 0 to 4 to 0. What about the y piece? What is it at -2?
0.
0. What about 2?
0.
What about 1? 0. What about 0? 0. What about 1? 0. Okay. All right. We're not surprised by this. So of course, let's put some intermediate stuff. What about 1/2, for example? So what's sine of pi over 2? 1. So then I basically know everything else. Are you guys okay with trig enough? I mean, it's going to have to, if it's up there between those, it's going to be down here between those, it's going to be up there between those. That's how sine works.
Wait, why is sine pi? Why is it 0? For the when you input 1 for t, why is it 0?
Sine gives you the y side of the triangle in the unit circle, right?
Yeah.
So if I'm at an angle that puts me on the x-axis, I have no y component.
Oh, okay.
So at pi, that's -180 degrees. I'm on the x-axis. There is no y piece.
Oh, yeah.
Okay.
Sorry.
No worries. So it's doing this.
Straight up.
Weehaw. Woo. Okay. I'm sorry, should have stopped it too. I went a little overzealous. Okay. So I expect my x to do this, 0 to 4 to 0. while my y is going 0 to 1 to 0 to negative 1, so 0 to 1, right? So the end result, well, let's see, can we do this really quickly? See what the end result would be. Of course, that problem is a little bit easier. They give you the functions. Maybe I should pick one of those examples. Let's do this as a real quick memory thing. So we already have everything we need. Actually, screw this. We can do this. When t is negative 2, what's the point? You can put them together, right? Does everybody see how when t is negative 2, I get 0, 0. The x is 0, the y is 0. When t is negative 1, Jeff, good job, buddy. When t is negative 1, x is 3, and y is 0. I should do the intermediate, maybe. Maybe. When t is negative 1/2, I get, I wanted this to be quick, but negative 3/2. I'll get something gross here. Oh, this is taking too long. No. Let's just do one other book here. Okay. Put this up on the overhead. Just real quick, just so you understand, that's not difficult. You just have to make a TXY table. It's just trying to make it quick. But it's not going to be quick. Just look at one example from this problem. This is problem number 30 in section 10.1. Okay. Oh, good. All right, so real quick here. So this problem gives you, let's see if I was looking at this right. Okay. This problem gives you, for example, it gives you the t versus x, t versus y. So what are the x values for this part A? What are they doing? What's the lowest the x value can be for this one? 1. And then it goes to 2 and comes back to 1, correct? So some of this could be by process of elimination. So if I look at my possible graphs to compare it to, does this one work? What did we just say? What's the lowest x could be for this problem? What's the lowest x could be? 1. Why does that not work? Man, this thing is so sensitive. I'm going to get sick looking at that. Sorry.
X goes to negative.
Yeah, so x goes negative, correct?
Yeah.
So screw this guy. He's no good. Nothing. First, what about this one?
No.
Same problem.
Yeah.
Yeah? All right, let's look at the other options. What about this one?
Can't see it.
Yeah, x went from 1 to 2
Yeah.
to 1, right? So do you see that how this one x goes from 1 to 2? Sorry, 1 to 2 back to 1. Do you see how that's what x is doing? And let's double check. What is y supposed to do at the same time? Go from 0 to 1 to 0 to negative 1 to 0, right? Y goes from 0 to 1 to 0 to negative 1 to 0. Do you see that?
Yeah.
Oh, yeah.
Okay, so this one's easier than what I was trying to do, to be honest, because they give you the end result. You can just kind of, sometimes it's process of elimination, sometimes it's got to, so you look at the x, look at the y, make sure it all matches up. I think the more interesting problem would be possibly between these two, because you see how x goes basically the same and y goes the same. They just go between them in different ways. You see that? This one should be, which one of these do you think should have more trig involved?
Top one.
Yeah, because it's doing a lot more trig in both dimensions. It looks like it's doing some trig stuff. This one looks less triggy, right? If you want to make up a word. No Will Smith, all that stuff. Okay. So, I mean, look what x does here. X goes from -2 to 0 to 2 back to, I mean, it's just all over the place. And look at this guy, for example. See how x is going from 0 to 2 to 0 to -2? And you see how y is going even more insane? Maybe. And then this guy looks like it should end up with less crazy stuff happening. Okay, so one way you can tell. This one looks to be bounded in both dimensions, both x and y. It looks to be a little more sine, cosine waves, both happening in both directions at the same time. All right. The first thing I would do, process of elimination, right? Example number 33. Anything that has negative x's, again, you can eliminate them. I'm sorry, I'm looking at this wrong. Anything that has goes more than -1 or 1 on the x-axis, you can eliminate them, right? So I would do a process of elimination first. Is that better? Okay. All right, maybe. Anything else from homework stuff? Yeah, I'm glad I got a few more people. That's nice. I like it. Okay. Before I forget, I want to show you guys, because I think several of you said you're going to take Calc 3 next. I want to show you one really good, cool thing. One thing that gets people down about Calc 3 is all the 3D graphing you have to do. So 2017 is apparently the last time I taught Calc 3 because Nick was a student of mine and he was also taking computer science courses. So he actually developed this program to graph things. So look in the corner here. You see the formula for this? Z equals x squared plus y squared minus 10. So as I move in the xy plane, whatever point I'm at, I input the x, I input the y, and the output is z. You guys semi with me? So if I make z a constant, don't I get a circle? If I make z 0, don't I get x squared plus y squared equals 10? Isn't that a circle? Right? So do you see how this is the 0 line? This is the 0 height for z. This would be up and this would be into the ground. So this is like the xy plane, and in that plane, it's just a circle. You can actually see the cross sections. I don't know if you guys can see that. You can turn this up. This is really a pretty good program. Anyway, so I just want to show you. It's called plot.ninja. So if you go to Calc 3, there's all these different 3D graphing stuff. A lot of them suck. Some of them are good. This one is really good. Anyway, just keep that in mind for your Calc 3 stuff in the future. Anything else from homework stuff? Will you guys try the homework out? I know at least one person has. They've turned some stuff in. Okay, all right. So last time we did parametric calculus, which is a nifty phrase in itself. That might scare somebody away. Tonight we're going to review polar coordinates real quick. Oh, and a real quick word about, remember that one problem, I still haven't found an adequate, something like that. Remember that one? We came up with a negative number. I was going to do it two different ways, and the first way is to realize that it's symmetric. I know my picture doesn't look symmetric. My poor little whale has been through a rough life. So if you just do from 0 to 1, and double it, you get the whole area, and that keeps it from going negative. I still haven't figured out exactly why you can't just do -1 to 1 like we did. So I'm still going to kind of look into that, but one way I was going to do it was to double just the top half. and the other way was to do it the way I did it. I just have to figure out why it came out negative. I still don't know. And to be honest, I forgot to look into it until right before class when somebody reminded me. I'm like, oh shit, I didn't look. Okay, so don't worry about that problem. So I want to remind you guys, how much does anyone remember anything about polar coordinates? Anybody remember hearing about polar coordinates?
Yeah. Is it like the magnitude and the angle or no?
Okay. It's like the distance to yeah. Okay. So think of this room as the XY plane. Each of you are a dot in the XY plane, correct? So if I wanted to get to Emily, let's say this is the origin, right? Because that's where I am. Let me go here so I can actually move. Right, I want to get to Emily. I could count how many spots up and how many spots over. That would be like Y and X. So that's our standard Cartesian coordinate system. Move this far over, move this far up. Yes? That's how you get along in a city like that's actually laid out in a grid. This many blocks over, this many blocks over. Yes? Okay. That's old and busted. Okay, so what's a different way that I could get to Emily is I could say, somebody could tell me, all right, turn this much, walk this far, right? Do you understand? X, Y is how far do I move left and right and how much do I move up and down? Of course, we all know that shit. That's not the only way to get to a point in 2 dimensions. You can turn and then walk a certain distance. It's not ground shaping, but again, it's not something we do all the time. And in fact, does anyone know where that system is used? Right now, a ton of people are using it at this moment. Anyone?
GPS.
Say again?
GPS.
GPS, okay. And that kind of relates to the thing I'm thinking about is if you're in a boat. Don't you set a heading?
Yeah.
And then go for a certain time to get somewhere? They're not going, no, they're freaking turn this way and move this much, yes? And if they're off by like 1 degree, after 7 hours, you are way far away from where you're supposed to be, yes? So when you turn a certain angle, you better turn the right angle, or else you're screwed. Oh shit, okay. So we got the XY plane, blah, 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 boring shit. So if I want to find a point in space, I can go so many over and so many up, or down, or back, so forth. Polar coordinates just says, okay, that's great. Same point. But now, lower, I want to tell somebody to give them a spot, turn this much, and then go this far. R theta. So instead of moving X over and Y up or down, I tell them to go turn this far and move by that much. I get to the same point, don't I? The whole purpose of the XY coordinate system was just to identify points in a 2-dimensional plane. That's it. That's the whole purpose. It is not the only way to identify a point in a 2-dimensional plane. You got this way too. Just like, is anybody born that wants to tell me in a different country? Anybody? Did you use pounds and did you use feet and inches? Or was this a long time ago? Maybe you were little when you moved? I don't know.
Yeah, I was really.
I got you. At this moment, do you guys know how many countries on the face of the earth use feet and inches and pounds? 2. Which one? It was 3. And the other 2, one of them just recently finished, and the other one I think is almost finished converting. And of course, America, we're special, we're probably never going to convert. Right. What's the purpose of feet, inches, versus meters and centimeters? Don't they both have the same purpose? Just to measure distance, right? These both have the same purpose, to find a point in space. So if I have somebody talking about kilograms, I need to have a way to convert it to pounds if we're talking to an American, yes? In fact, real quick, did you guys know there was the Mars, I think it was the Mars Polar Observer, I always forget which one it was, crashed into Mars because one group was using feet and inches and so forth, and the other group used metric. So one group programmed something, and of course, okay, we got time, but holy shit, I thought we were far away from the planet. No, do you guys know that? That's a little bit of money lost because of a wrong conversion. So polar, can somebody tell me, if I know the XY coordinates for this point, and I do, this point is XY. The polar, of course, is r theta, but can we figure out what it is in terms of x and y? What is r in terms of x and y? What is this in terms of x and y? What kind of triangle is
Oh,
this?
this is right. Isn't it tangent?
Don't overthink it. No, I don't care about the angle. Trig functions relate angles to side lengths. My question right now, I just care about the side length, right? I like it. So r, let's do r squared is x squared plus y squared. Right? Okay. And then, now come at me with something about the angle. How does the angle relate to x and y? What's the trig function that relates the angle to x and y?
Tangent.
Tangent.
Tangent y over x.
Tangent theta.
Oh.
So theta is the inverse tangent of y over x. Cool? Okay, so what if my point, so here's the first example. This is sort of like going from our units to everybody on the face of the earth, right? So of course we're going to have to talk about how about the opposite way. How do I do it the other way? So we'll get to that in a minute. If I know the rectangular coordinates, so in rectangular coordinates, I know it's, let's say it's, let me give you a good one. Sure. 1 comma square root of 3, 11. Can you figure out what the polar coordinates of that would be? And of course, what's the polar coordinates in general? R theta. How do I figure out R? Square root of x squared, blah, 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 blah. So take a minute, figure out what it is, figure out what R is, given that, and figure out what theta is, given that. The theta you should not need a calculator for. We'll see. So this is x and y, correct? This is rectangular. R. What do you get there?
2.
Yeah, you get 1 squared plus the square root of 3 squared, which is 3. Square root of 4 is 2, 11. So this point rectangular, so far it's this point polar. Whoops. So to get the angle, go ahead and try to get the angle. Again, you shouldn't need your calculator. And you're like, don't trig shame me. No, come on, you shouldn't need your calculator.
Isn't it 30 degrees?
How? Why do you say
Sorry.
that?
No, not 30. 60
There it is. And really, again, I don't know how you were taught trig, but you can see from this picture, which dimension is bigger, x or y? We know from the beginning,
Oh, y.
y is bigger, meaning this angle should be bigger, yes? If the y was smaller, it'd be closer to the x-axis, so it's not 30, it's 60. Yeah, so this would be the arc tangent, theta would be the arc tangent of y over x. The way I remember tangent goes like sine because sine's on the top of tangent. Tangent's bigger when sine's bigger. Sine's bigger at 60. Square root of 3 is the bigger option. It could be square root of 3 or square root of 3 over 3. I don't know if you guys are with me at all. Right? So tangent goes like sine. Tangent's bigger when sine's bigger. That's the bigger thing, so it must be the bigger angle, 60 degrees. because the y piece would be bigger, which is pushing that up, and it's getting closer to the y-axis. Okay, maybe. Okay. So that would be, give it to me even better, radians. Pi over 3. Yes. So therefore, this point in rectangular would be this point in polar. So this point tells somebody, walk 1 over, and then root 3 up, and you'll get to the point, right? Dig there, and you'll find something. Okay. This one says, screw that shit. Turn by an angle of pi over 3 radians, 60 degrees. Turn by that angle, and then walk 2 out, and then dig and find the treasure and all that shit. Either way, you get to the same point. So part of this could be, I don't know if anybody out there, if you're really following me, if you're thinking to yourself, why the hell do this shit? Don't we already have a way to find a point? We can find a point, Jeff. There, you just go 1 and rad 3 and leave me alone. But the whole point, like I said last time, is certain problems are really difficult or impossible to do in one coordinate system, and maybe it's easier or possible to do in the other. So the more coordinate systems we know, the more problems we can do. I like it. Kick ass. By the way, this is a little huge for those of you going into 281, because you're going to basically take polar and make it into 3 dimensions.
So you said a problem could be easier using polar. So if we were given a problem where we have to plug in an x and a y, would we just plug in an r and theta instead?
Yeah. So we're going to get to a point where we might have to integrate x squared plus y squared or something. Well, this would be more like what you would see in Calc 2, but let me think about what would we see here. Calc 3, I'm sorry. Off the top of my head, I can't. That's the first thing I think of because I've been tutoring a lot of Calc 3 today. So I'm kind of stuck in Calc 3 mode. But there could be an integral where you have the square root of x squared plus y squared inside of an integral, correct? Don't you agree with me that that integral would become much easier if I can replace that with r? What do you think about this integral versus this integral?
Okay, yeah, that makes sense.
Right? And that's a really rough sketch of an outline of the idea. But that's a good example of what I'm talking about, right? Depending on, if the problem itself is inherently circular, it should work better in polar. If the problem itself is inherently straight lines, it should work better rectangular. That makes sense. You guys with me? So real quick, if I were to extend polar, do you guys see how polar is basically circular? Yes, real quick, all right. Here's one thing. Hopefully you guys all got this. This is the huge thing right here. Let me do this. Here's a really good question that you should be wondering about. If I have x, y coordinates, it's relatively easy to plot them. But if I give you this, and I say plot this, why is that harder to do? It's not too hard. Can you guys tell me, could you make this an approximate where pi over 4 is? Basically, turn by pi over 4. That's diagonal, yes? That's easy. Now, walk out in that direction exactly 4. Would you go here? Why does that make sense? If I'm pointing pi over 4, how far do I go? Would I go this far? Is that 4? Did I move 4 out in that direction? Come on now. Did I move 4? This is way longer. If I push this down, isn't it going to go past 4? This is way longer than 4. Do you start to see the problem? Right? Why is it so easy in xy coordinates? Because the xy plane is 1, 2, 3, x, 1, 2, 3, y, and then I can find freaking points. I just go blah, blah, blah. So what do I need here? I actually need axes that agree with my coordinates. What the shit? So what I mean is, if r equals 1, what do you think that means? The radius is 1, correct? Mm-hmm. Did I tell you which way to face? No. So you face every direction you can. Sort of like if I said graph x equals 1 on a xy plane. How would you graph x equals 1?
Just 1 on the x-axis.
Would you put a circle, a little dot? No. There it is. Why is that the answer? Because what does this say about y? Does it constrain y? Is there any constraint on y? All I give a shit about is x is 1. What can y do then? Anything. So here, this says r equals 1. What can theta do?
Be anything.
Anything. So 1 that way, 1 that way, 1 that way, 1 that way. So here's r equals 1. Right? And what would this equation be in rectangular coordinates? What is this equation? X squared plus y squared equals 1. Which equation looks better?
Equals 1.
That one looks better, yeah?
Yeah.
Shit, yeah. Okay, and again, it all depends on what the situation is, but the more tools we have, the more ways to identify locations in space, 2D, 3D, whatever, the more problems we could do. Because there are certain problems that are impossible to do in one coordinate system, but if you translate it, you can do it in the other coordinate system. Okay, so that's r equals 1. So watch this. I want graph paper that has one axis. So here the axis is x and the other axis is y. Here one axis is r. Okay, what the shit? So this is r equals 1. This is r equals 2, right? R equals 3. That's pretty good for me. That's bad, but it's good for me. Now it's easy. Now, what else do I wish I had indicated here? What if I wanted to graph? So 4 pi over 4 would be relatively easy here. I just have to go one more dimension out. There's pi over 4, there's 4 pi over 4. You with me? A little bit? Okay. What if I wanted to graph 2, 5 pi over 6? Is that getting a little trickier? Why was pi over 4 relatively easy? Why was pi over 4 relatively easy? Because I just have to go in the middle, yes? Why is 5 pi over 6 not going to be that easy? I can approximate it, right? It's not right in the middle, for one thing. It's going to be closer to what? Which coordinate? Which quadrant am I in?
Second one.
Second. Closer to which axis?
X-axis.
X-axis is pi over 6 away. It's 1/6 of a pi away. So it's going to be like right there. But is that 30 or is that 15 or is that 27 or is that 35 degrees? Do you guys know? Do you understand? And again, don't freak out. What other thing then do we wish was on polar graph paper?
The unit circle.
Be more specific. I think I know what you mean.
Angles.
Angles, yeah, right? So I want there to be like a pi over 4 here and a pi over 3 here and a pi over 2 there and blah, not 3 there, Jeff. Pi over 6, pi over 3. Right? Okay, I like it. So the r-axis is each of these circles. The theta axis is moving around the circles. Really weird. Different from what we're used to. But here's the other thing about this. Hopefully you guys have picked up on this. The less comfortable you are with trig in general, this is going to suck, right? So hopefully you guys are not as bad with trig. Hopefully you had some time to kind of like beef up on your trig a little bit. This is going to be very trig heavy. Okay. So let me come back to something. So I'm going to give you some polar graph paper in a minute. And this will be the last time I give you any. You got to go find your own, damn it. But if you want, I can post on Canvas. In fact, I should do that. Somebody will remind me. I can post on Canvas. The one I use, it's the best one I've found. There's a lot of other types, though. So, let's come back to what we have so far. If I'm given x, y, I can find r theta by using these relationships. You can write this as r equals square root. The reason I don't, let me ask you this. One reason I don't write that as a square root is because could I ask somebody to turn to a certain angle, look that way, so I can say, okay, turn by this much, and now walk backwards? Yes? That makes sense, right? So R could be negative. That just means face the angle and walk away from it, right? Face the monster, go, oh shit, and start walking backwards, right? Maybe? You don't want to turn your back to the monster. Okay. It's calc / monster fighting class. Okay.
So if you could do that, why wouldn't you just only use the top half of the unit circle to give everything?
Well, because you need your end result. Points exist down here. If I'm given that point, I need to be able to identify it.
Yeah, like couldn't you just say, face something in the first quadrant? And
But then if I walk backwards, if I face this way and walk backwards to get to that point, I still need this to exist.
Okay.
Yeah. I like it. So, before I give that out, let's do this the other way. What if I'm given r theta? How do I find xy? So let's kind of draw the situation. I'm given, or can you guys see that color? Okay, sorry. Oh, let me try this again. I kind of like creamsicle, but it doesn't really show up. Given, well, now you can see, but you can't read. I understand. My beautiful handwriting. Find xy. So I'm given r theta. I'm given this, and I want to know what that point is in terms of x and y. Can somebody tell me, so isn't x just the length of this side of the triangle? Can somebody tell me?
Oh yeah, isn't it cosine theta?
All right, now put the whole thing together. What's cosine theta?
Cosine theta equals x.
No. What is cosine theta of this triangle? What's cosine theta equal to? What two sides? It's a ratio of two sides always,
yeah.
right? That's all trig is.
X over R.
X over r.
Yeah.
So isn't x equal to r cosine theta?
Yeah.
Okay, now real quick. This is the thing. See if you guys are cool with this. Does everybody agree with me that in this geometry, okay, I'm not going to say it like that. Like this, isn't the x and y, aren't they both smaller than r? In a right triangle,
Yes.
x and y would be smaller than r.
Yeah.
Beautiful. This is not true, but it is useful. And this is the way I looked at it when I was first taught this. And it got me through a lot of physics and shit. Cosine theta is the percentage of r that lies in the x direction. Do you see that? If I multiply r, how do I do 10% of 20? What would you do? 0.1 times 20, yes? And then blah, blah, blah. So cosine theta, isn't it less than 1? Absolute value, right? But still. So I see cosine as being the percentage of the hypotenuse that lies in the x direction. So if I want to know what the x piece is, it's the hypotenuse times cosine theta. The percentage of r that lies in the x direction. It really actually isn't, but that's kind of a cool way to think about it. So what's the y piece going to be?
R sine theta.
R sine theta, because sine theta is the percentage of the r that lies in the y direction. And again, for all my physics and math people, I know that's not true. I don't care. It's a useful kind of little way to look at something. Not a damn thing wrong with that. Yeah, maybe. Okay, and that's it. Believe it or not, that's the conversion. That's it. That's awesome. So, given, let's do an example. Given, what you got, Jack? I don't know, man. 6, sure. Negative pi over 4. I love it. Convert that to rectangular coordinates. And real quick, somebody tell me, what is 6? R. And what's negative 5? Theta. Okay, so convert those to x and y. Which is just like me asking you, 26 inches is how many feet? You got to convert it. And we have a formula, and here's the formulas for converting. So x will be
Is it 4.24?
6 times cosine negative pi over 4. I don't want decimal answers. You should not have to use your calculator. Yeah, cosine of pi over 4 is rad 2 over 2. Cosine of negative pi over 4 is the same as cosine of pi over 4 because they're basically the same exact length between those. You guys with me? So what I always remember about cosine negative theta, cosine of theta versus cosine negative theta, they both talk about exactly the same x piece. Whereas sine of theta versus sine of negative theta, they talk about one's the negative of the other one, right? Okay, so this will be 6 times rad 2 over 2, which is 3 rad 2. Okay, and y will be 6 sine negative pi over 4. Like we just said, this will be negative 6 times rad 2 over 2, which will be negative 3 rad 2. So this becomes 3 rad 2, negative 3 rad 2. So see that, well shit, why'd I have to pick 6? Damn it. real quick. I can do that. Let's see. Yeah, let's do it by 2s. 2, 4, 6, right? Negative pi over 4, so it's about here, yes? And then I want to go out 6, so that would be about right there. What is 3 times rad 2? Now give me a decimal because I want to kind of graph it by hand. What is 3 times rad 2?
4.24.
4.2. So do you agree that the x piece of this looks to be about 4.2? Yes? Even on my shitty scale? You guys understand? So it's the same stupid point. I can either call it 6 negative pi over 4, or I can call it 3 rad 2 negative 3 rad 2. It's the same stupid point. So what's negative 3 rad 2? It would be negative 4.2, that's negative 2, negative 4, negative 6. Now here's where my scale gets really bad, but I won't. It's too bad for me, but still, it would still be on a nice, beautiful polar graph paper, it would be exactly the same. So let me give you that, since I keep talking about it. I have at least one paper for everybody, maybe more. One side I put 3 and one side I put 2, just in case this side is too small for your eyeballs. Okay. I have enough for 2 of these for everybody. You're gonna need polar graph paper for your homework. Yeah. Or we're gonna use some of it right now. Another one. I think I have enough. Let's find out. How's it going?
I'm still open up.
All right.
We got 10 minutes to go here.
I have exactly the right amount. Sort of stuff's ready. Oh, good. I got it. That's right. So let's take a look real quick. I want to do some really, really basic stuff. So, as I said, you've got your R-axis. So you see how this one is darker? That's like supposed to be 5, right? So 1, 2, 3, 4, 5. You can change your scale if you need to, like I just did. You can make this 3, 6, 9, 12, depending on what you have to plot, right? There's your radians going all the way around. Yeah. So where is negative 11 pi over 12?
Pi over 12.
Well, sure, not really though, because it doesn't quite go all the way around, right? So here's 11 pi over 12, correct?
13 pi.
So if I go this is 11. Yeah, negative 11 pi over 12 is just 13. So you can kind of. So where's negative 5 pi over 6? There. You guys see what I'm saying? Maybe. Okay, so let's do this. Let me give you this sheet here. I forgot I had one of these on here. Let's do number 2 first, just to do that. I have 15 million of these. All right, so. Please, dear God, please do not try to use notebook paper to plot polar points. My God, right? I don't care how neat you are, they don't. Right, so just get some polar paper. I'll put it up in Canvas so you can print that one out. Or you can Google polar graph paper, right? And just copy it, print it out from there if you don't like this one. So let's do a couple quick ones and I'll let you guys do the rest. 3 pi over 3, how do I find that? What do I do?
You go to pi over 3 and go 3 out.
Yeah, you face pi over 3. And then you just go 1, 2, 3 up. Right? That's too nice to believe. 1, 2, 3 up. Real quick, let's do this because this is a much nicer paper. Can you guys please take a minute, figure out what the x and y are for that? Right? Go ahead and give me decimals. Feel free to just throw this in the old calculator.
1.5.
Say again?
1.5 for x.
1.5,
Yeah.
roughly? Okay.
Oh no, it's just 1.5 exact.
Oh, okay. Oh, yeah, of course, that makes sense. And then this was going to be
Sine
the
is 2.59.
2.59?
Yeah.
Okay. Does everybody agree with that?
Yeah, almost 2.6.
Well, somebody out there is like, I don't know, just waiting for somebody to do it. Okay. So real quick, watch this. All right. This is a much better graph to do this on. This point is 3 pi over 3. 3 pi over 3. So face pi over 3, go out 3. It is also known as 1.5, yes? 1, 2. So 1.5 on the x-axis. And then how far do I go up? I go 1, 2, 0.5 roughly, a little bit more than 0.5. You guys see that? That is 1.5 comma 2.59. It just is. It's just a point on a two-dimensional thing. Humans have just created at least 2, and you know there's more, at least 2 ways to identify where the hell that is.
Wouldn't it be 2.6 because it'd be rounding after 98?
Well, I don't know. I just stopped at 9. So 2.6, even better. Thank you.
I said because physics and he says must round up if we're gonna stop.
Definitely. I just crowdsourced it, so I was just going, yeah, so that would be 2.6 apparently, yeah. I like it. So every circle is 1, right? So this is 1, 2, so this is 1.5 on the x-axis, right? This is 1, 2, 3, so this is 2.6 roughly on the y-axis, right? Okay, there you go. Much better than the picture I tried to draw myself. Okay, maybe. Again, we have points in space. I'm going to find them. I'm going to tell other people where they are, right? Real quick, let's do, well, here, you guys do the rest real quick. Just hurry up, come on. No, just do the rest of those. Sorry, you don't have to do it. Try to plot this. Oh, by the way, oh dear God. If you have a problem, you're plotting several things. Holy shit, label those things, yes? I get problems turned into me in homework, there's just dots everywhere. I'm like, no, what are they?
It's a very cool picture.
Yeah, and then you gotta connect it. Makes a face, sticking his tongue out at you. Or makes a Stanley Cup, right? Does anyone remember doing this in pre-calculus? Huh? Oh, I'm sorry, man. Shit. Everybody else got one of these? I seem to have decided to skip people. Oh, okay. I also seem to have left the people at home out. Okay. So the next point's pretty straightforward, right? You face 3 pi over 2, and you go forward 1, 2, 3, 4. One way to think of this real quick is if you take the XY plane and you curve it, you get this, right? Can you imagine breaking this up? And then you get the XY plane? Anyway, okay. They're all pretty straightforward, 3.5 pi. So you face pi, and you go 1, 2, 3.5. Kabam, yes? All right. Keep going. Is everybody cool? I really want to make sure. I almost don't want to say this. Is everybody cool about why that's there? Okay. I'm not even going to say what else because I don't want to miss you. So again, it's kind of, I always thought we should have made this theta comma r, because what you really do is you face theta first and then you move r, but oh well. Face pi over 6, and we go out 1.5. Yeah, buddy. What does that mean? Where do I face for party? What do I look at? 2 pi over 3. I look in this direction and I go back 3. Now, real quick, sometimes it's hard to tell which line is back. Do you see what I'm saying? It's sort of like those weird optical illusions where you gotta see, here's one string, where's it coming out the other side? I don't know. Just the pi over 3 is gonna go with the pi over 3, right? So if you're supposed to go back from 2 pi over 3, you know you're going the right way if you're going towards another over, it's hard to do it when you're looking that way, over 3, yes? Do you guys get that? Okay. And eventually we are going to be making patterns and connecting the lines. They won't make the Stanley Cup, but they will make some other shapes. And how the hell do I do this one? Say again? Yeah, to go back 11 pi over 12, I'm actually looking at 13 pi over 12, so I'm going to face this, and I'm going to go 2 out. Now, real quick, looking at part E, is there another way to represent that point? Look at this point right here. Is the only way to represent point E like this?
No.
Because what am I actually, what, instead of walking backwards, couldn't I get to the same point a different way?
Yeah.
What would I face? Instead of facing 2 pi over 3, I would
5 pi
face
over
5 pi over 3. So another way to identify that exact same point. And of course, then I would walk. If I face 5 pi over 3, I'll walk 3. Right? So instead of facing away from 5 pi over 3 and going backwards, I could just face 5 pi over 3 and go forwards. Couldn't I then rewrite each of these with a negative r the same way?
Yeah.
What's a less interesting way to write a different point for this? Well, let's look at this one. Right? This is the boring shit. You're gonna like, Jeff, it's all boring shit. Oh, come on. All right, everybody agree that's boring? 3 pi. Where's 3 pi?
Pi.
Pi, right? So 5 pi, 7 pi. That's more boring. That's the whole idea of a terminal point. You can just have a lot of rotations, right? You remember that? Subtract 360, subtract, holy shit, how many 360s are there? You remember defining the terminal point? Yes? You're like, what is 8,528 degrees? Oh, get away from me with that. Yes? Yeah, if I positive 11/12 is this, negative 11/12 is going through the same angle, so I would stop here. That's all, yeah. So if I want to go negative 5 pi over 6, I would just go there. So 5 pi over 6 is there, negative 5 pi over 6 is the mirror image. Because I'm just turning the opposite direction. Okay. Maybe. Okay. Now to be really honest, I thought it would make a lot more sense to teach this right after you did the unit circle, right? But oh well. Let me think. Anything else I want to say about this one? Where is this point? Yeah. In fact, if I put 0 comma anything, isn't it the same? It's the same point. If I say, okay, face 4 or 13 pi, now don't go anywhere. Oh, shit, man. Why did you make me twirl around? Right? So 0 comma any damn thing is the origin, correct? Okay. Let me see if you guys get this. So again, what would this look like? R equals 3. What would R equals 3? What would that equation look like?
Circle.
X squared plus y squared equals 3.
Yeah, not even in rectangular, just what would the graph look like?
Circle.
It's a circle. In fact, doesn't that just say radius is 3? And again, theta can do whatever it wants to, so that would be 1, 2, 3. That would be this circle here, right? What do you think this is? Theta equals pi over 4. Yeah, what is R? Does R have to be anything? R could be anything, as long as theta is pi over 4. So wouldn't that be everything on that line, including? So that would just be this line, correct? You see that? Can anybody tell me the rectangular equation for the line I just pointed out? Is everybody pi over 4, right? It's every point that has theta equal to pi over 4. So it's every point along this line, yes? What's the rectangular equation for that?
Y equals pi over 4x.
Good try. Y equals x. How do you know that? Because pi over 4 is exactly
Oh, 45.
halfway, and that's y equals x, yes. So watch this. You ready? I don't know, Jeff. Watch. Here's a really cool thing. Remember tangent lines? You guys remember tangent lines? Do you remember learning about tangent lines and going, why the shit are they calling it tangent? Isn't tangent this other thing with the trig stuff and the shit? Yes. Did anybody ever tell you what the hell tangent? Why we call it tangent line? What is tangent of this? If I take tangent of both sides. What's tangent of pi over 4? What's tangent of pi over 4? 1. And remind me, tangent of theta in terms of the conversions. Look at the top of the paper. What's tangent theta?
Y over X.
Multiply by x, don't you get y equals x?
Yeah.
Right?
Oh, yeah, yeah.
Tangent of the angle that the line makes equals the slope. So of course we call them stupid tangent lines. Tangent is the slope. Right? In fact, one thing your teacher could have told you is tangent's y over x. Isn't slope delta y over delta x? Okay, but that's sort of this is really kind of cool. So if I make that pi over 3, tangent of pi over 3 will be the slope in the equation of the rectangular version, right? Maybe? Okay, sorry. I'm wrapping a lot of things in together, but they all just kind of like come together right now. Over here. All right, so real quick. I keep saying real quick. Do 1 AB and 3 AB because they're sort of the same idea. And again, you got your conversions up here. And by the way, you do have to memorize those. And why is that not hard? Because you've already got those memorized for the most part, right? Those are just facts. We're just using them in a different way than we're used to.
Which one do you want us to do? Number 1?
1 AB and 3 AB. This one we almost did earlier, but switch your. So number 1. Pretty straightforward. Right? And you guys have met me, so you know I'm not going to want any freaking decimals on these answers, right? Because I'm an asshole. But, so, real quick, what quadrant would this end up in?
3.
Quadrant 3. So what should the sign, SIGN, of x and y be?
Negative.
It should both be negative. Cool. So all I care about is the reference angle, right? Because I already know the sign. That's all I have to care about. The reference angle tells me what the number is going to be. So I know the answer is going to be negative. What is the cosine of pi over 3? Cosine of 60. Cosine likes x. The further it gets away from x, the more scared it gets. The smaller it gets. It's a half. I love it. So this will be negative 2 times 1/2, so it'll be negative 1. So what about sine of 60?
3 over 2, so
Yeah.
2, it would just be 3.
So it'll just be negative rad 3, right? Because the
Negative.
2's cancel. Okay. So one thing you can do when you're doing this stuff is just make sure that the answer the point you get is in the same quadrant as the original point. Yes? Okay, I like it. And yeah, this is more. This is the same freaking way gives a shit. Yeah. What's the reference angle here? Pi over 6 is the reference angle, 30 degrees, correct? What quadrant is this in?
Third.
Why do you have to be careful? Well, it's not the third quadrant. It's not the third quadrant. It's the first, because you face this angle, but you go backwards. So you guys see that? So I know whatever I get as my answers, they better both be freaking positive, because I'm in the first quadrant, yes? Okay, cool. I almost don't care what the answers. It's just a bunch of, just who cares? I don't know, maybe we should. So, x equals, let me see if you guys understand what I'm about to do. I'd much rather just go ahead and call this 12 pi over 6, yes? That's the same point, correct? And that makes this so much easier, because now it's just going to be 12 times cosine of pi over 6. So it's 12 times rad 3 over 2, so it's 6 rad 3. And y will be 12 times sine pi over 6. 12 times a half, so it's just be 6. Is that cool, you guys already? You'll get the exact same damn answer if you use this, but understanding that you can call it a better thing. You can make the work easier on yourself by just rewriting what that point is represented as. Hell yeah, I'm going to do that. And then, now this is a little more interesting. This is where you have to be careful. We basically did that problem earlier. It's just this turned around, so I don't care about it. Let's do part B. What quadrant do my r theta have to end up in? What quadrant is this in? Second quadrant. Back, up. Yes? So I better end up in the second quadrant. So let me just put that over here just to remind myself. Quadrant 2. Jeff? Okay. So how do you get r? Let's do r squared. What do you get?
X squared plus.
Yeah, x squared, so it'll be 2/4 plus 2/4. Is that cool? Half plus a half, so 1. Figure out what r is in a minute.
R is 1.
How do you get theta?
Arctan.
Yep, arctangent of the ratio of these, which is -1. Does anyone know what the arctangent of -1 is?
Is it 45?
Sure, but it's not 45, right? It's the wrong quadrant.
135.
Oh, 135? Sure. Give it to me in radians.
3 pi over 4.
3 pi over 4, okay. So, I would have also accepted negative pi over 4, right? You guys see that? What two quadrants is tangent negative in? Second and fourth, right? Is that right from your perspective? I think so. If you choose 3 pi over 4, what does r have to be to make sure I'm in the second quadrant? So I'm facing 3 pi over 4. Do I want to go forward or backward to be in the second quadrant? Forward. So r would have to be 1. If I chose negative pi over 4, r would have to be -1. I really want, and see, that's r squared, correct? When I take a square root, isn't it supposed to be plus or minus? Very often when that happens, it's because the humans in the situation have to pick plus or minus. Right? The algebra is stupid. We're the smart people. We're the smart things that created algebra. We have to know when I take a square root, which sign do I need? Since you chose 3 pi over 4 for the angle, that's got to be positive 1. Remind me why that is. Why does this have to be positive 1? If that's 3 pi over 4,
Because it has to be in the second quadrant.
has to be in the second quadrant. Big ass. I love it. I enjoy it. Okay. Real quick, anybody have your calculator out? Can you do the arc tangent of -1?
-7.
Ah,
Oh wait, -0.78.
yeah, which is negative pi over 4. So this is what I'm saying. Do you remember, real quick, since this is going to come up, inverse trig functions, their outputs are limited. Why? Because in order to make inverses exist, I couldn't have the whole sine function. I couldn't have the whole tangent function because they wouldn't pass the horizontal line test. Yes? To have an inverse, you have to have something that passes the horizontal line test. So for tangent, for example, I had to chop it. All the infinite tangents? No, no more above pi over 2. No more below negative pi over 2. I could just have one so that it will pass the horizontal line test. So when I do arc tangent, it can only give me an angle between negative pi over 2, pi over 2. Does that mean that's the answer? No, that's the reference angle. Again, we're the humans. We have to know what the hell to do with it. So if you do that in the calculator, you get negative, you would have had to make this r negative so that you end up second quadrant. Are you guys with me? Again, I don't want to make this feel like it's extra work. No, it's trying to checks and balances. Okay, maybe. So let's try out the funkier stuff. Let me do a simpler problem with you real quick. If I had x squared plus y squared equals 5x, is that one problem I have? Sort of. I've already got that problem, Jeff. All right, let's do this one first. X squared plus y squared equals x. I want to convert that to polar form. Well, what is x squared plus y squared in terms of r and theta? R squared, yeah. So I can just replace that. That is r squared. What is x in terms of r and theta? What is x equal to? You can look at the top of your sheet, right? R cosine theta. Why is this sort of not a good place to stop? Not just because I can't make the letter S, but why is that not a good place to stop? Is there a simple thing you could do to simplify this?
Yeah, you bring r to the other side.
Divide by r, yeah. So what do you get?
R equals cosine theta.
Anyone know what this is the equation of? A circle, yes? But what kind of circle? No, I see what you're doing. It's radius the square root of x, but that's not good. Yeah, because the square root of x is many different things. I would have to complete the square and all that kind of shit, yes? To see what the, in fact, let's do, all right. Since I'm getting some blank stares, I'm going to do it. Nah. Let me write it again. Okay, stay with me. You ready? I'm going to subtract the x. Gotta make some room. Remember completing the square? How do you complete the square? 2 steps. Nobody? Anybody? Yeah, like what do you want from me, dude? All right. Take half of the middle coefficient. Step 1. Step 2 is square that. This is what I add. Now if I add it here, I better add it here, yes? This is what this factors as. Does that feel familiar to anybody? So tell me, what 2 things do you know? What's the radius of this circle? No? Thank you for playing.
Origins left.
Okay, good. Okay, where's the center?
Negative half.
No. Remember transformations? Doesn't every input I put in have to be 1/2 bigger? Because the first thing I do to it is take half away. That's why it actually goes the other direction than what this makes it seem. It's gonna move to the right 1/2. Is it gonna move up or down at all? No, there's nothing with the y. So the center is at 1/2, 0. And the radius is the square root of this, because this is r squared. No? Yes? So the radius is 1/2. So, if I plot, what do we get? R equals, what do we get? Yeah, R equals cosine theta. What is the center of that circle?
Wait, 5?
1/2. Isn't that what we just got?
Yeah.
What's the radius of the circle?
1/2.
Freaking 1/2. Check, of course, because both equations are referencing the same collection of points. That's all an equation really is. It's just the definition of a collection of points. So if I have two different ways to identify points, I should end up with two different equations that identify the same set of points. So, yeah. So this equation here, holy shit. Okay. This equation here references the same points that this equation does. Just using a different coordinate system, just using a different way to kind of point people in directions. That's all. Sorry? So this is the rectangular coordinates that represent the circle. In fact, let me see if I can this handle two coordinate systems at once. Oh shit. Let me see if it can. That would be really cool. Yeah, I think it can. Shit and a half. There we go, Jeff. I know you can't see this one. Equals 1/4, okay. Okay, there's r equals cosine theta, right? That's the red one. If I turn this guy on, perfect. Of course. They're the same equation. It's just like somebody saying, well, you have to move 12 inches that way. What? You mean a foot? Yeah, a foot, sure. Didn't we just say the same thing?
Yeah.
So if you say this and I say that, we just said the same freaking thing. I'll stop beating that point, I'm sorry. I really want you to understand. Okay. So, what about this here? How could I convert that to polar? What is y? R sine theta. What's x? Or cosine theta. And then you can kind of multiply that up. Is that cool? If you stop there, that's okay. Does anyone? Oh, no file exists. Oh man. Is it really cool? I just multiply that up, right? Good Lord. Does anyone have a suggestion? Can I write this a little bit more compactly? Anybody know how to write this more compactly? What's 2 sine theta cosine theta?
Sine 2 theta.
So what's sine theta cosine theta?
1/2
1/2 sine 2 theta. So I can write this as 1/2 r squared sine 2 theta equals 1. Either way, I would take either way. Okay, so going from rectangular to polar normally is the easy way to do things. So let's look at the other type here. I want this to make all the sense in the world. If you see a sine theta and you're supposed to convert to rectangular, what do you wish was in front of it? because it'll go right into a rectangular coordinate system. Say what? I heard somebody say something. R, yeah, because if there was an R in front of this, well, that's zoomed in way much. If there was an R in front of that, what would it be? If there's an R in front of the sign, what could I put there? What's R sine theta?
Why?
Y. Okay, cool. Is there an R there?
No.
Shit. How do I make an R show up there?
Multiply
both sides by R. So again, a big part of being able to do math problems is to understand what's the motivation. Right there, it's very simple. If only there was a frickin' R there, oh, I can make an R show up there. So what's R squared?
X squared plus y squared.
And what's R sine theta?
Y.
And again, if I wanted to, I could pull the 5y over, complete the square, figure out what that is, blah, blah, blah. Do you remember how the cosine theta was on the x-axis? So the sine theta is going to be on the y-axis, and it's going to have a radius. Well, let's see what you think. Just looking at it. Turn that guy off. Take this 5 sine theta. Holy shit! Oh yeah, zoom way. Now the circle, here's something interesting. The circle has a radius of what?
2.5.
2.5, 11. R as measured from the origin, what's R as measured from the origin to get to the other side of the circle? 5. Yeah, okay. But the radius of the circle that this function creates is 2.5. Okay. Okay. Oh, that's the one that's a little more interesting. Let's see. We sort of talked about this earlier. You guys remember what this would be?
It's gonna be a straight line.
Straight line. What's the slope going to be?
Oh, wait.
Well, I mean, it's going to be the tangent of pi over 6, right?
Right.
Yeah.
Which is going to be, so again, tangent's big when sine is big. Pi over 6 close to the x-axis, sine small. This is rad 3 over 3 when you take a tangent. Yeah. So this would be tangent theta equals rad 3 over 3. This is y over x. This is y equals rad 3 over 3x. So again, you understand better now why we call them tangent lines, because when we analyze stuff, the tangent basically tells me what the slope's going to be. So again, math people are not very creative with names. Tangent, slope, tangent line. Okay, let's see. How much more can I squeeze in? I wanted to let us out early, but Shaisa, I do have to do at least. All right. Damn it. So take one of your little papers that I gave you, drafting papers. Did everybody get a couple of papers with a bunch of these drafts on it? Or did somebody? Can somebody please let Ricardo have one of yours? Okay. All right. Thank you. All right. So the last thing we're going to do for today, unfortunately, let's do it, is we're going to remember how to plot equations on here. And I want to plot the equation. Let's do this. I want to plot the equation r equals 2. Let's make it r equals 4 sine 2 theta. So just like when you learned X, Y, the first thing you learned was how to plot points. The second thing you learned was how to create points given an equation. And then you learned how to plot the equation as a graph by plotting points and connecting them, right? So we're sort of doing that quicker because we all know math a lot better than we did then. So we just learned how to plot polar coordinates. Now I'm going to plot an entire function. So does anyone have a suggestion on what I would do to try to start to plot this by hand?
Do you want to split up sine to theta or no?
No, it's just going to make it a little worse, to be honest. I'd rather evaluate one trig function instead of two each time, right? So if you're faced with a function that you don't know what it looks like and you have to graph it by hand, you start by creating XY table, right? So in this case, I'm going to make a what table?
R theta.
R theta. Now what sucks is, now you're going to understand better why I wish we would have called polar coordinates theta, comma, r, because what's actually most often our input? Theta, right? So I'm going to be picking numbers here and calculating this, but oh well. So what's a good place to start? 0 is a great place to start.
0.
So yeah, sine of 0 is 0, cool. Let's try to go by pi over 4. Let's see how, let me think. Let's see how, should we? Shit. That might, screw it. We'll try pi over 4.
4.
Yeah, sine of 2 pi over 4, sine of pi over 2, so I get 4, correct? Probably gonna need more, damn it. I'll be fine. Pi over 2, what happens there?
0.
0 again. Then if I do 3 pi over 4, then I get sine of 3 pi over 2, correct?
Mm-hmm.
What's sine of 3 pi over 2? 3 pi over 2, sine,
Oh,
negative 1.
yeah.
So negative 4 here, right?
Yeah.
Negative 1 times 4. So you can see the pattern, and you can see why maybe we need better resolution. Remember when we learned parametric? And I said you might have to start putting things in the middle of things you've done. So I should have left room, but oh well, it's too bad. I didn't. So then if I go to pi, 0 again, right? And it will just continue like that. So let's try to do some intermediate ones. So what about pi over, let's try pi over 3, sure. This is where it's going to be really good to know a few values really quick. So what do I get sine of 2 pi over 3, right? That's still positive because it's still where the y-axis is positive. The reference angle is pi over 3 is 60 degrees. What's sine of 60 degrees? Rad 3 over 2. I like it. Because again, sine likes it when it's close to y. So the closer y gets, the bigger the output is for sine. Times 4. So it'll be 2 rad 3. Yes? What is 2 times rad 3? I think it's 3 point. I should know this. I forgot. 3.4?
3.46.
Yeah. So rad 3 is 1.73 roughly. 1.7. So 2 rad 3 will be about 3.4. It's really about 3.5. So when I'm making you graph things by hand, and again I will do that because I'm a jerk. It's okay to round to the first decimal place. Good Lord, I'm not going to be able to graph them by hand correct to the second decimal place. How you guys feeling so far? Everybody with me what I'm doing? I wanted better resolution. I mean, is this really, this doesn't seem to be telling me enough information in the middle. I don't know how it's getting from 0 to 5. I don't know what it's doing in the middle, just like with parametric. So I'm putting a few things in the middle of these. Right? What's in the middle of pi over 4 and pi over 2? Pi over 6. No, pi over, did I put that in the wrong place? Jeff, my God, I already did pi over 3. Oh my God, Jeff, you are tired. That should be in here. That's my problem. It should have been pi over 6. Dadgummit. Oh well, let's see. Can I save this? Yes. Jeff is tired. So in here should be pi over 6. We already did pi over 3. That would be in the middle of those two. So this would be 3.5. And I'll bet you. So if we do pi over 6, do you see how it's pi over 3 again inside?
Yeah.
So it's 3.5 again. So it would have been fine, Jeff. No. So real quick, let's see if we can capture what's happening so far. We don't have every point yet, but let's see if we can capture what we do have. So 0, 0, okay, that's easy enough. 0, 0, great. Then from there it goes to 3.5 pi over 6. Okay, so face pi over 6 and go 1, 2, 3.5. And then from there it goes to 4 pi over 4. So face pi over 4 and go out to 1, 2, 3, 4. And then at pi over 3 it went to 1, 2, 3.5 again, right? And then it goes back to pi over 2, it goes to 0 again. So I'm going to face pi over 2, but I'm going to go nowhere. So it does this. Do you guys see that? Or I guess maybe you don't. I'm going to pick something better. Maybe purple. I don't know if that comes up any better. That's a little better. Okay. You with me? And if I needed to, couldn't I capture the direction I'm going to? So I'm going, I came from 0 and I went out and then I came back. So I'm probably, now here's when things get interesting. And of course, I'm leaving so little time. So let's do, so we ended up at pi over 2, correct? Let's do 2 pi over 3 next, just to see what's happening. Because we did 3 pi over 4. Let's do 2 pi over 3. So that becomes 4 pi over 3. What's the sine of 4 pi over 3? Again, the reference angle is 60 degrees, correct? So that's rad 3 over 2, but it's going to be negative. So it's going to be negative rad 3 over 2, which is negative 1.7 roughly. So, where am I at? Yeah, times 4. Oh, where am I at? Wait. 2 pi over 3, that's rad 3 over 2. Now, why did I say 1.7? Yeah, rad 3 is 1.7, rad 3 over 2 is 0.8. Oh, screw it, just put in your calc there. It's getting too late. My brain is going crazy. So yeah, so it'll be negative rad 3 over 2 times 4. There we go. Which is negative 2 rad 3, which is negative 3.5 again. So if I face 2 pi over 3, whoops, where'd my, there we go.
Back one.
This is the first one? Yes, thank you. If I face 2 pi over 3, I actually go back 3.5. So now I seem to be, so remember I went like this, came around, and now I'm coming through 0, and continuing. Now I really don't have to do much more work here, because I'll bet you anything, just like this one went to 3.5 and then went to 4, where do you think I'm going to go next? I'm going to go to 4, aren't I? And then I'm going to go back to 3.5, and then I'm going to go back to 0. So where do you think it's going to go from there? So now I'm coming down, around, and I'm going to go through 0 again. I'm going to make another one of these just symmetric to that, yes? Okay, so now I know at my pi over 6, I'm going to be at the 3.5, 1, 2, 3.5, and then I'm going to be at 4, and then I'm going to be at 3.5. So a lot of these work this way, where once you get a few things, you can sort of use symmetry to finish it. You don't have to make a complete table. And then I know, now watch, I'm coming through 0 again, aren't I? So now I'm going to come through 0, and then I'm going to do it all again here. My pi over 3 is going to go to 3.5, then 4, then 3.5, just like it did before. I'm going to end up like that. You went to 5, Jeff. It's all right, buddy. You're tired. I'm going to cry. Okay. Forgive me. But what I really want you to take away from this is when you first start to graph these, you can think, oh my God, I'm going to make this big-ass table. No. Because of the repetition of trig functions, you just have to do enough to see where it's going to go from there. What was the multiplier inside the function? It was 2, right? What did this 4 do? All that 4 does is what? You can do. What's in front of a trig function? If I have a number in front of a trig function, that just affects its amplitude. So all I did was kind of like zoom in on the picture of it. So that 4 had nothing to do with what I'm about to say. How many leaves did we end up with?
4.
4. What was the inner number? 2. So real quick, lastly, I keep saying real quick, it's always a lot, sorry. 4 sine 2 theta. Okay, so there it is, all its glory. So what do you predict will happen if I put a 3 in there? Not what you thought. Where'd the other 3 leaves go? They actually overlap those leaves. So every odd multiplier inside ends up with that many leaves. Every even multiplier, if I put a 4 there, now do you know how many leaves? 8. So if I put 11, how many leaves? 11. If I put 12, how many leaves?
24.
Yeah. Funkadelic, yes? Okay, I like it. And again, all this does is just makes it bigger, smaller. It doesn't affect anything else. It's just the amplitude. And again, do you guys understand what I'm saying when I say, dear God, I hope you get into Desmos or something. Just play. Just play with this shit. Okay. I'm really sorry. I'm really tired, so I made a few mistakes, but hopefully it's okay. Oh, here's the practice test. Unfortunately, my printer is going on strike or something. It's trying to negotiate for better working conditions. So, not everything quite printed on this graph. What? So when is the next test? Oh, the final? Okay. Okay. The next test is
It's next week. 18th, right?
a week from today.
Oh, wait. 17th?
17th. Yeah. I like it. So I'll have the answer key for this. I'm probably going to make 10 for extra credit. Well, we'll talk more about that next time.
And also, there's no quiz in between the test?
Well, it can't be, because next time is review day.
Oh, yeah.
Yeah. So if I was going to give a quiz, I would have given it today.